Hi everyone, we're moving on to internal energy now. And internal energy is something that you need to be awake for and in a good frame of mind and concentrating to kind of grasp, because it's something that's, I guess, not very, something that you won't have thought about probably from the things that you've kind of experienced in real life particularly. But hopefully when I talk you through it, it's gonna, if we're concentrating properly and I do it in a logical way, it's gonna start making sense to us. If you've got a solid, and I was doing this in the last video, and hopefully we all were kind of watching those with interest, engaging in it and what have you. You draw a particle theory diagram for your solid. And we know that these particles are moving around, and that actually, the more they move around, the hotter they are, or if we heat them up, they're going to move around more. What we measure when we measure temperature is the average kinetic energy of these molecules. Okay, so the temperature is average kinetic energy of molecules. That's what we're measuring. So temperature is a measurement of average kinetic energy, right? That's a kind of fact that we need to be able to grasp here. Hopefully that makes sense to you. The more these particles are moving around, then the larger the temperature we're going to measure. We'll keep that fact on here because we need to keep thinking back to it as I'm going through. If we heat this up, then we heat it up to, let's say it's ice, and we heat it up to 0 degrees. We're putting in energy all the time, okay? And that energy is going into the average kinetic energy, right? When we put in energy into this, it's not just going to disappear. It goes into the average kinetic energy of these molecules. They're moving around more, which means that the temperature is larger, so we've got an increase in thermal energy overall. But at 0 degrees, what's going to happen is this structure is going to start to break up, and we're going to end up with a random arrangement of particles that can move around over each other, our particle theory diagram or kinetic theory diagram for a liquid. To get from here to here, these particles have got bonds between them, forces of attraction is a better thing to say actually. They're not chemical bonds necessarily actually, as in you might have inside molecules in chemistry, but they're forces of attraction between molecules. And to get from here to here, they have to break, right? They're a bit like those the springs that I had in the last lesson, or maybe you can imagine these are magnets. But they have to break apart, and so to do that, we need to put in some energy. So whilst we're heating this ice, to get from here to here, we need to put in some energy. But what that energy has gone into breaking these forces of attraction, or into overcoming the forces of attraction, is much better language actually. I'll try and say that. Overcoming the forces of attraction till we get to this stage. It hasn't gone into the particles physically moving around more. And therefore, the temperature doesn't go up whilst the substance is melting. So we're going to plot a graph of that. Let's say we've got energy that we're putting in. And there, this is temperature. Plot a graph of that. So we get our ice out of the freezer. Freezer's probably set at minus 18 degrees. They normally are. Something similar to that. And we're putting in energy, and the temperature is going to increase. But when we get to 0 degrees, I should say this is in degrees C. When we get to 0 degrees, the temperature doesn't increase as we put in energy, because when we put in energy, as we move this way, the energy that we're putting in is increasing. The energy is going into overcoming the forces of attraction, and so the temperature stays the same because no kinetic energy is added, and therefore the temperature stays the same because temperature is a measurement of average kinetic energy. And if we keep going back to this fact, then this stuff starts to make sense. After it's all melted though, if we put in some more energy here, then actually we can increase the average kinetic energy of the molecules in the liquid water. And so this will happen. As the temperature gets to the boiling point, so 100 degrees, the same thing's going to happen. the energy that we're putting in has got to go into overcoming these forces of attraction, this force of attraction that hold the water together, the gas that we're looking to get. It's like this. Sorry, I've drawn off the desk here. But to get from here to here, we need to overcome the forces of attraction that are between these molecules. So we've got very weak forces of attraction in the gas state. So we put in energy to overcome those forces of attraction means that the average kinetic energy of these molecules isn't going up, and so the temperature isn't going up. And then once it's all steam, we can then increase the average kinetic energy of these molecules, and we end up with a graph that looks like that. These flat points, we've got the melting point and the boiling point. It's very hard to replicate a graph like this in real life because I've got energy on the x-axis, and how can you measure the energy that you put in? It's very difficult to do that, especially as the hotter the substance is. So the steam up here will be cooling down in the room, so you have to have to get a perfect graph like this, you'd have to have not only increase the temperature of the water, but also make sure that the room was always the same temperature as the water to get a perfect graph. So it'd be very difficult. But anyway, so this is the two types of energy that a substance holds. And it kind of makes sense. Steam at 100 degrees has more energy stored in it than water at 100 degrees. Or water at 0 degrees has more energy stored in it than ice at 0 degrees. And we know that because you've got to put in energy to melt the ice. So there's two types of energy involved in a substance. Just going to rub this out. Every substance in the universe, I suppose, has got the kinetic energy and the potential energy. So if we add those together, that'll be the total energy in the substance, and we call it internal energy. So internal energy is the total energy in your substance, and so it's kinetic energy plus the energy that is gained from or used even to separate the molecules or the particles to overcome those forces of attraction, and we call that potential energy. A bit like if I've got this pen on the desk, there's a force of attraction between the pen and the earth, and if I put in some energy, I can overcome that force of attraction. Right, so this pen has now got potential energy. That's gravitational potential energy. This type of potential energy is actually very similar, but it's not gravity that the potential energy is overcoming. It's the forces of attraction between molecules. I guess, so we call it potential energy. So internal energy is kinetic energy plus potential energy. I guess you could say internal energy is kinetic energy plus forces of attraction, potential energy, if you wanted to, because we say gravitational potential energy is the kind of mirror of that. But we just strip it all down and write potential energy. Hopefully, this all makes sense to you. If not, I'll post something on the post board, and if you're in my class, I'll get back to you. If you're not, then your teacher will get back to you. So we're going to try and answer some questions on a grid. I want you to fill out the grid. It's talking about these particle theory diagrams that I was drawing, but also where the increase in energy is if we increase the energy in a substance. So fill out that grid, and then there's a flipped around physics sheet as well to do. Thank you very much. I hope you're all doing well.